So when we're talking about dilations, we need two pieces of information. When we dilate a figure, we need to know the center of the dilation that we are working with, and we also need to know the dilation factor. Now, if you think way, way back to 7th grade and the WUMPs, you dealt with scale factor. Well, a scale factor is pretty much the same thing as a dilation factor. It is how much we are enlarging or shrinking a figure. If we have a dilation factor that is bigger than 1, you'll end up with a larger figure. If you have a dilation factor that is less than 1 but greater than 0, you'll end up with a figure that is smaller. But it's also possible to have a dilation factor that is negative, which is actually kind of a fun thing too, but we won't worry about that right now. All right, so a point of dilation is the point that the dilation originates from. And if I'm writing it, what are you doing?
You should write it too, Pastor.
Thank you, John.
Thanks, John.
I know, right? Just because I have this microphone, no one wants to say anything, right? I'm glad that you're such a good cheerleader, Trip. Okay. So the point of dilation is the point that a dilation originates from. A dilation factor, this is pretty much the same thing as a scale factor. And that is the factor that we're multiplying the side lengths by. All right, so what we're going to do here is we are going to dilate some figures all by ourselves. Now, how many of you have played, well, let me ask this. What kind of, where have you seen a dilation happen in your normal life? Elliot? Mugwumps, we definitely dilated. Nice connecting it with 7th grade. Trip? That sounds like video games. How do you say games? Juegos. Juegos. Am I saying it right?
Sure.
Thank you. All right. What type of video games rely heavily on dilations? Not necessarily all of them, but there's a specific type of video game that you particularly probably enjoy playing that relies heavily on dilations. No, these will be your 3D games. Although, I mean, everyone loves their Pong, but I don't think anyone's playing Pong at home anymore. Yeah? Zelda.
Yeah, that's actually true. Yeah, dilation. Yeah, that actually is true.
So when in Zelda does it happen?
All the time.
That's not helpful for someone who doesn't play Zelda.
When you move.
When you move, do you get bigger or smaller?
Yes. Well, like depending on how close you are, it will get bigger or it'll get smaller.
So do you have an avatar in Zelda, or are you the avatar? Like, yeah.
Okay. I should go after he finishes speaking because I have
Let's hear your whole different game because I feel like I'm going down a rabbit hole.
Well, you know those really bad mobile games where you walk and you collect things and then get bigger?
Okay, yeah, that would definitely be a dilation where you like walk over something and you get bigger. Okay. All right. All right. So what kind of video games have dilations all the time? Sorry, Nate, what did you say? first-person shooter games?
Why would that be?
Well, so in a first-person shooter video game, the perspective that you're looking at the screen is the perspective of a person, right? So this is a first-person view, and and typically things are running at you, yes. And as they get closer to you, they get bigger. Is that what you said? Kind of? All right. So first-person shooter games rely completely on looking on dilations to look realistic. Because as the figure comes closer to you, they get bigger, and so that dilation factor is multiplying over time as objects get closer. Yes, right?
Yeah, yeah.
That's what you were going to say?
Yeah.
Uh,
That happens in Roblox too.
Okay.
No, trust, actually, no,
I know.
murder for sure, bro. First person, oh my god. Like, dude, oh my.
I feel like I'm giving Riot a platform. Okay. So anyways, so dilations are critical when we talk about video animation. So here we go. So we're going to dilate this triangle. Why are we dilating a triangle? Because you love triangles. No, because it has the fewest number of vertices of any object. So it's less work for you. But you can imagine having a space alien and enlarging it. That would be more fun, but more work. So we're not going to do that. But here we go. So we're going to dilate this triangle from the point -7, -7 using a factor of 2. So the first step that I'm going to do, and there's nothing on your Chromebooks right now that you need to look at. Thank you very much. We need to locate point -7, -7. So let's go ahead and do that on our grid. So -7, -7. So I'll go 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down 7. 1, 2, 3, 4, 5, 6, 7. And I'm going to make a dot so that I know where this point is. Have you located -7, -7 on your grid?
Nope.
Not yet. All right, let's do that for you. All right. So the next thing I'm going to do is I like to provide something that I refer to as projection lines. So we are going to create some lines that appear to be coming out of, appear to be coming out of our center point, our point of dilation. So I'm going to make a line, and you're going to use a ruler that comes from the point of dilation through each of the vertices. And I would make those lines as light as possible. A straight edge is definitely going to be what you want to use. It doesn't have to be a ruler. A simple straight edge would do. Now, these lines are going to help me locate my next points because I know that the dilation, the vertices in this dilation, are going to be on this line. So, once I have my projection lines going, I am going to count from my point of dilation to a vertice. It doesn't matter which vertice I start with. I'm just going to look at that one right now. So from here to here. So how far over did I go? How far to the left did I go? -1. That's right. I went to the -1. I went negative direction, so it's left, -1. All right. How far up did I go? It's on your paper, so if you can't read the board. Thank you for the one person who's able to count to 5. Storm cash for you. Storm cash for you. All right. And so now I'm going to multiply both of these values by a factor of 2. So -1 times 2 is -2. So my new point is going to be over 2 in the left direction. And then I'm going to multiply 5 times 2, which is 10. And then from the point of dilation, I'm now, instead of going -1 and 5, I'm going to go -2 and 10. Well, here's 5, 6, 7, 8, 9, 10. Oh, look at that. It's on my construction line. Isn't that nice? All right. So then I will repeat that process for my other 2 points. From the center of dilation to this corner right here, the closest corner, how far over, how far up? Over 1, up 2. So we got that's +1 and 2. So +1 times a factor of 2 is 2. All right. 2 times 2 is 4. So I'm going to go over 2 and up 4. Oh, look. That's right. That point's right on my projection line. So right now, I would like you to locate the third point. Locate the third point. Who's your fantasy partner? Emma, is it Emma?
Well, yeah.
All right, so for fantasy. All right, so where is the third point in our triangle? 3, -3. So let's double check. So 3 over, 1, 2, 3, 1, 2, 3. So right here. Can I get someone to confirm that? You can confirm that? Okay. So just to double check, so that is, how far over did we go? We went 1, 2, 3, 4, 5, up 2. So now we're going to go over 5, up 2 from here. 1, 2, 3, 4, 5, 1, 2. And there we go. And so now we're just going to connect the dots. And do we have a shape that looks like the original? Yes. Is it the same size? Is this congruent? I don't know. Are these shapes congruent? No. Are they similar? Yes. So now we have a similar shape and the side lengths are doubled. So this is not a rigid transformation. A rigid transformation is a transformation that preserves the size of the object that you're transforming. So this is not a rigid transformation. There's an R here. So we end up with a transformation or a image that is no longer the same size as the original. Are there questions so far? Okay. In that case, I would like you to try to dilate the figure on the bottom left.